Man, of course, has been counting and computing for many thousands of years, and his inventiveness has led to the creation of devices to aid in calculation. Sand tables, knots in ropes, and notches in sticks. And one device still in use today, the abacus. In all calculation, there is a 5-step pattern consisting of input, storage or memory, the arithmetic operation, control, and output. Classically, the control element is the human being himself. But in the digital computer, control is achieved electronically in strict conformity with instructions provided the machine by the human programmer. The great power of the computer resides in its ability to carry out whatever arithmetic or logical operations the mind of man is capable of instructing the machine to perform. There is a popular tendency to personify computing machines as giant brains and to endow these remarkable inventions with many human characteristics, including neuroses. The fact is that the computer is a tool in the same sense that the wheel is a tool. However, an important difference between the wheel and the computer is that we, the humans, can instruct the computer to imitate the behavior of any other specific machine or process, providing we can adequately describe what we want imitated and can instruct the machine in its own terms how to carry out the imitation. This does not mean that a computer can become a chemical plant or even a wheel, but it does mean that when we can adequately describe in mathematical and logical terms what goes on inside a chemical plant, we can simulate this on a computer. It is this characteristic that permits us to call the computer the universal machine, in that it is capable of doing whatever we are capable of instructing it to do. J. Presper Eckert, the Vice President of UNIVAC Division, Sperry Rand Corporation, comments on this.
It's a new tool. I've been present at several computer centers that were dedicated at universities. And I've tried to think, well, what can you say this means to the university? It means something to the math department, it means something to the physics department, it means something to the economics department, and then it's hard to find where to stop, because in principle you can even study some things about music on a computer. In fact, simple tunes have been composed on computers, as you know. It seems to me that a computer is the first general purpose tool we've had for some time. And at a university, I think it's the first general purpose tool the university has had since the library.
Although the automatic digital computer has been in existence only since the mid-1940s, the blinking lights and the spinning tape reels have already become tiresome cliches symbolizing one branch of modern technology. However, when we think of a computer as one product of man's technological ingenuity, we usually fail to realize that the computer represents a fundamentally different kind of advance from other recent technological advances such as atomic reactors. The difference lies in the fact that the computer manipulates not energy, but information. We asked Dr. C.R. DiCarlo, Director of Education for the International Business Machines Corporation, about this difference.
Well, I'd like to comment on the two main streams of technology. It seems that first is the use and the development of enormous power that we have today. Power such as the atomic and nuclear energy, the power of the jet engine. These are manifestations of the continuing use of energy to amplify man's muscular ability. They go right back to the development of his first tools and up through the first industrial revolution, the development of power machinery. And by and large, I think people can accept both the understanding and the consequences of the use of physical power. The other mainstream is more subtle. It concerns itself with information. And the information we have in our bodies, the information that we receive from the outside world, is a very intangible sort of thing. It's hard for us to conceptualize it as a physical phenomenon. And yet this new technological revolution really concerns the very nature and the uses of information. For example, in the development of the computer, we have, in a relatively short time, I think 2 or 3 decades, come up with equipment which can solve problems far in excess of the range capable of solution by human mathematicians and physicists 100 years ago. We've seen these computers applied to problems in business, in science, and government, and they seem to put a great many people in awe that the machine is doing something near human, near thinking. Actually, what the machine is doing, of course, is handling information.
It is information from the senses that brings the world to us. And information about the things, events, and processes in the world can take many forms and can be communicated in many different ways.
Federal Reserve Board Index.
As much as the presumption of
It is a
continuance.
genuine tragedy. First quarter. There'd be a third quarter dip if there were a steel strike. This is well above. The new rug you asked me to deliver to your home last week.
Cannot introduce expert testimony.
Dear Mrs. Ransom, enclosed is a bill for the new public construction.
It is information from the past that helps us better understand the present. It is information that permits us to take the right action at the right time. And it is information that permits us to predict the future state of a system. And when information can be quantified and expressed in the symbolism of arithmetic and logic, and manipulated in accordance with the rules of mathematics and logic, we have the means to control, to design, and to simulate any real-life situation we can adequately describe. And the digital computer is the tool by means of which these manipulations, running into millions and millions of separate steps, can best be carried out. Of course, the answers and the decisions that you get out of a computer are entirely dependent upon the data and instructions you put into it. Unless the set of instructions, or program as it is called, is carefully and accurately thought out, the computer cannot possibly come up with the desired answer. There is an interesting expression among computer scientists that goes GIGO, G-I-G-O, garbage in, garbage out.
If you put garbage into a machine in the way of data, garbage will come out. And not only that, it'll come out faster than garbage has ever been generated before.
The only way to avoid the generation of meaningless information is for a human programmer to figure out in advance the exact sequence of logical steps necessary for the machine to operate properly in relation to a given problem. Once this logical design is laid out, It must then be communicated to the machine. And it must be communicated in a language that the machine can understand.
This is a field that's ripe with all kinds of emotional connotations which have always bothered me. The idea of man-machine communication implies, in a sense, an equivalence of man and machine. I like to think rather of the machine and the system as amplifiers and sensors of man. And if you view them this way, in general, you have the problem of connecting the world of symbols and abstractions which men deal with, which are very complicated, with the symbols and the operations with which machines can deal. These symbols and operations are extremely primitive, they are simply binary numbers, that is, a series of bits of yeses and nos, and nothing more. So we have the problem then of communicating this world of symbol and abstraction, which is very complicated on the part of the individual, to a very primitive machine. Now the question is how to relate these two, and this is at the heart of this problem of, quote, man-machine communication.
The so-called language of a digital computer is limited by the possibilities inherent in an electronic circuit which can be switched on or off. Internally, the elements in a computer have only two possible states, on or off, which can mean 1 or 0 in the binary number system. The off or on state can also represent yes or no, true or false, and so on. A binary number consists exclusively of ones or zeros and combinations thereof. In the binary system, each place means an increase by twice as much rather than 10 times as much as in the more familiar decimal system. In the decimal system, we would write the number 33 with a 3 in the tens position and a 3 in the units or ones position. In the binary system, 33 is written with a 1 in the sixth position. This has a value of 32, and a 1 in the first position, which has a value of 1. 32 and 1 equal 33. This may seem like a terribly awkward way to express numbers, and it is when you're using pencil and paper, but it isn't when you're using an electric voltage. Given its two possible states of off or on, there is no other way to express numbers in an electronic computer, and there is no known number that cannot be expressed in the binary number system. Information in number form and instructions in number form according to a prearranged code can be handled in a computer at a rate approaching the speed of light. However, a major problem is encountered when we undertake to convert the high-level abstractions of human language and logical and mathematical formulations into the bit-by-bit language of a computing machine. Dr. Richard Hamming, research mathematician at the Bell Telephone Laboratories, comments on this.
Well, it should be realized that it is the man who has the problem, not the machine, and it is necessary for the man to communicate to the machine what he wants done in some mutually understood language.
Dr. DiCarlo.
The principal problem today in getting a, quote, machine language is getting the users of machines to agree upon the symbols and abstractions they use to define the problem. So number one, there's a problem of standardization of our symbols and abstractions among people. This is entirely independent of the nature of the machines we're dealing with. The second problem is having attained such a degree of standardization of symbols and abstractions on the part of the people using machines, to develop some system to convert these very complicated and highly charged symbols and abstractions into the primitive nature of machines. Now, machines are very primitive, and they differ one to the other. So we would like a process which takes our symbols and abstractions and converts them one by one into the various and different machines that are available today.
Fred Grunberger of the RAND Corporation.
We're going to increase the brute force of the machines by quite a bit, increase their speed, we can go perhaps another order of magnitude without too much trouble. A more important advance there would be the improvement of our languages. We need better means of communicating with the machine. Now, where we go from there is a real good question, because we are already pushing the speed of light quite hard. There's an upper bound to how far we can go with sheer brute force speed. I don't think there's any upper bound in the improvement of our languages, just the ability of humans to do it.
Obviously, in science and in mathematics, we have a language. We have a set of symbols and abstractions which have found general universal credence and credibility and acceptance. Therefore, programming in the scientific field, because we have this agreed-upon set, has proceeded much faster than in the field of business. In the field of business, or in the use of our machines in human affairs, you're dealing with procedures which are described as a result of human understanding of words, human understanding of procedures, human purposes, which are very complicated.
One of the most important areas of research in the computer field today is the design of special languages for man-machine communication. These programming languages, such as Fortran, Flomatic, Algol, Cobol, and Jovial, aim at symbolic simplicity, application to a wide range of problems, and translatability into the specific digital number language required in the many different kinds of computers. The reason for developing these languages is to permit the human programmer to state the problem he wants the computer to work on in a language which is closer to what human beings would normally use in stating the problem. Once the problem has been stated in the special language, the computer itself, following instructions permanently stored in its memory, translates from the special language into its own microsyllabic or digit-by-digit language. Using these special languages allows the computer to take over much of the painstaking and detailed work that once had to be done by the human programmer. Use of these languages, however, does not eliminate the necessity for the programmer first to understand the problem and then to work out the logic for its solution. But he no longer has to write out this logic in the bit-by-bit language of the machine itself.
One of the things it seems to me that's clearly evident, that if you talk about a machine having a language such as Fortran or Jovial or autocoder, you semantically confuse that with the idea of language, English, French, and Russian. One should be very much aware the purpose of languages as we use it among ourselves and among people is to cover a whole range of experience where the words are highly charged, where sometimes even silence conveys more information than the most explicit statement. And to use language around man and around machines without appreciating this difference, I think, is the cause of some of the problems we have in personifying machines as being humanly capable.
Of course, some people will always think of a computing machine as a device with a little man in it who does arithmetic and answers questions. This particular man in the machine analogy doesn't tell us very much, except to point up the fact that what happens inside a computing machine happens in strict step-by-step sequence in accordance with instructions that are stored in the machine's memory at specific electronic locations or addresses. Now, so far as the inside operation of the machine is concerned, the problem being worked on could be anything from a payroll calculation to a nuclear physics problem to a simulation of the national economy. Whatever the problem, the machine must carry it out in minute step-by-step fashion. The key to the versatility of the machine rests with the instructions that are given to it. And when it comes to speed in carrying out these instructions, well, the whole analogy breaks down because our little man just isn't up to it. In only a few brief years, the electronic computer has progressed from an idea, essentially a mathematical concept, to the status of an indispensable tool in the sciences, in many businesses, and in industries such as the petroleum industry. In addition to being a prodigious keeper of records and a machine to control other machines, the computer is being used more and more as a tool to aid in planning and in decision-making. In theory, the computer is limited only by man's ability to instruct it. And there is research currently underway in what has been called the learning machine. In other words, in machines that improve their own performance based on their past experience with certain kinds of problems, such as checker playing. The most famous of these research experiments is the one being carried out by Professor A.L. Samuel of IBM.
I've given these concepts to the machine, but not told it whether they are important or not. And the program, as a result of its playing experience, decides on the relative values of these various things we call parameters. And by doing this, it changes the importance that attaches to center of the board, kings, and so forth. And as a result, it changes its playing techniques with time and actually improves.
Obviously, the objective in this research is not merely to develop a machine which plays a better and better game of checkers. Will the next development be a new machine or new methods of using machines? We asked this question of a panel of computer experts. Dr. Thomas Barron of the Shell Development Corporation, Dr. Ernest Koenigsberg of CEIR, Dr. Richard Hamming of the Bell Telephone Laboratories, and J. Presper Eckert.
We've got to develop new methods, and I think the new methods are more important than new machines, because I think once we know what the new methods are, we won't have much trouble rearranging hardware to fit them.
I think that all of us would agree that we have by no means exploited the machines we now have available, and that there's much to be done in learning how to use what we already have, although all of us would prefer better machines.
Assuming that we can, say, in the next 10 years, build a machine whose central computer is perhaps the size of a baseball or a grapefruit, we could probably build a machine in which the times of operation of the elements was in the order of a tenth of a nanosecond, that is, in the order of a 10/1000th of a second, a tenth of a billionth of a second. And presumably such a machine with improvements in logical organization could be 1,000 times faster than the machines we have now. But as we mentioned earlier, the machines we have now are 10 million, or 10 to the 7th power, times faster than an unaided human doing arithmetic. Therefore, having made progress of 10 million to 1, another 1,000 to 1 doesn't look like much. In fact, since progress probably is on a logarithmic scale of, let's say, doing twice as good every year or something like that, to use your figure, this means that at this rate, another 1,000 to 1 will just about keep up with our requirements for the next 10 years, because 2 to the 10th is 1,024. And if we're going to make any progress beyond, say, the next 10 years, then we've got to find something new rather than just turning the crank faster.
Well, I think the new ways to solve problems is far more important than picking up a factor of 10 or 100 in machine speed.
We all agree.
So that we have to learn how to use these tools well, and I think that's more important than looking for the next generation of machines.
The extension of the use of computers depends more on finding more imaginative uses of them rather than improving techniques for the uses we're putting them. Right now, I would say that most of the uses are technological, engineering or scientific in sense, making computations that we would have liked to make before, but we couldn't do them quite as accurately. Now, here we cannot hope for too much because we were already pretty good at doing them in the first place. Anyone can calculate trajectory, maybe not quite as accurately as the computer, but we could do it before. On the other hand, computers make possible calculations that we have never had the guts to explore before because of complexity. And I think the extension lies here. If you tell a businessman that by paying $1 million for a machine, he can improve his inventory position by 3%. He may or may not find this a very good deal, but if you tell him that this will tell him a new way to compete in the market, allow him to make decisions about tactics and strategy of business, or if you tell the government that here's a tool which will tell us something about a better social organization, or better tactical and strategic ideas about how to defend ourselves, then here are areas in which people cannot afford not to use them.
Most of the machines that man has invented have an obvious purpose and an obvious limit. But this is not the case with the computing machine. A computer is a tool that extends our problem-solving and decision-making power. Through its ability to handle information in accordance with our instructions as to how this information should be handled or manipulated, a computer becomes a truly universal machine in that we cannot set a limit to what we may be capable of instructing the machine to do. As we ourselves extend our abilities to describe events and systems in mathematical and logical terms, we shall continue to extend the uses of computers into these new areas of understanding and control. This extension of use, together with the computer's great speed, accuracy, and economy, has already produced and will continue to produce fundamentally new effects in business and industry, in government, and in science. Today, more than ever before, a wise decision depends upon the availability and the examination of great quantities of information. The computer is the first of man's inventions which literally enlarges the decision-making power within man himself.
If a computer can point out some of the results of different alternatives to the man or men making this decision, and do this quickly, the decision these men make will take more into account than if they made the decision purely on what they can see and hear in the ordinary way. And therefore, they ought to be able to make a better decision, one I would have more faith in. I disregard a man with a good tool as being able to accomplish more than a man with his bare hands, that's all. This is NET, National Educational Television.